Welcome to Mass and Energy. In 1895, Lorentz published some work in which he made several predictions that led to the special theory of relativity. One of those was to do with Newton's second law, and the idea being that if you want to accelerate a mass up towards the speed of light, then what should happen is that the force would increase toward infinity because the mass is increasing, which means that you can never get past the speed of light. A lot of the ideas that Lorentz had contributed directly to Einstein's paper in 1905. In 1964, William Bertozzi did some experiments on this idea. He used thermionic emission to create a burst of electrons that were accelerated up to a high speed by an anode. They then passed into an evacuated chamber several meters long and hit a target made of aluminium. This chamber was evacuated so that the electrons did not collide with any atoms on their journey. The target at the other end was made of aluminium. An electronic timer was connected to each end of the evacuated chamber. And this timer took the form of an oscilloscope reading, where a pulse was measured at the start and the end of the electron's journey. The difference on the x-axis gave the time, and the voltage used to accelerate the electrons could be used to calculate the kinetic energy that they had. This data was plotted on a graph. Newtonian physics predicted that as the kinetic energy increases, so would the square of the velocity, and there should be a straight line graph. They ran the experiment. The electrons were given off and accelerated by a voltage to a very high velocity. They entered the evacuated chamber, and the time of that was measured on the oscilloscope. They then travelled through the length of this chamber, which was several meters long, and arrived at the target. And again, this was measured on the oscilloscope. They could calculate the velocity because they knew the length of the chamber and the time difference between entering and hitting the target. And they plotted their results on the graph. 0.5 mega electron volts, 1 electron volts, 2, 3, and so on. They could even upgrade the equipment up to 15 mega electron volts, but it never went above 9 times 10 to the power of 16 meters squared per second squared. This limit that the data was approaching happened to be the square of the speed of light. The difference between the predicted and the experimental values was very large, and checks were made to make sure that all of the kinetic energy that they thought was being given to the electrons was actually going into the electrons. And they did this by comparing the amount of energy, the amount of work done on the electrons, with the amount of energy that was arriving at the aluminium target. They gave the aluminium target a thermocouple so that they could measure its temperature, and they measured the energy transferred to that target using the equation for specific heat capacity, and dividing that by the number of electrons that are arriving. And it was found that these were equal. All of the energy being given to the electrons was arriving at the aluminium target. You will recall that the kinetic energy of the electrons is half mv squared. And the Newtonian physics assumes that mass is constant and that the energy is going into increasing the velocity. That's what this line on the graph is predicting. But that's not what was going on. Mass started to increase the closer the velocity got to the speed of light. As velocity approaches the speed of light, the mass increases. These observations can be plotted on several graphs. On a graph of kinetic energy against velocity, we see the kinetic energy rising very slowly and then suddenly increasing. It never exceeds the speed of light. A similar graph of rest mass against velocity, that is, the mass of an object at zero velocity. At low velocities, the mass is close to 1, and then as we approach the speed of light, it dramatically increases, but never equals the speed of light. The total energy of a particle is equal to its kinetic energy plus its rest energy. And this rest energy is equal to the mass of the object when it is at zero velocity, multiplied by the speed of light squared, divided by a familiar term. This term at the bottom is also in the equations for time dilation and length contraction. When velocity is equal to 0, this term at the bottom is equal to 1, telling us that the rest mass is equal to E equals mc squared. The total energy is equal to the energy of a moving object plus the energy of the object when it has zero velocity. As velocity approaches the speed of light, this term approaches 0, which means that kinetic energy approaches infinity, just like Lorentz predicted. The closer an object gets to accelerating near the speed of light, the larger the mass gets, and therefore the larger force you need to continue accelerating it.